So thanks for coming to the session. I'm Steve Freeman. This is Nat Price.
Hello.
From London. Just a point of mechanics, because we're working in English. You don't want to hear our French. If anyone at the back or even the front is struggling with the language, just stick a hand up or something. So it's your money. If you can't understand us, we can't help you. Right. So, our background is, this is our claim to fame. This is our brief advertising moment. But this represents 10 or 15 years experience of the London community. So a lot of what we talk about comes out of quite a strong community of developers in London. And we're both sort of, these days, both independent developers, coaches, consultants, all that kind of thing.
Yes.
So now, commercial break over. Here's our question. So we see lots of people trying to do the right thing. And they're following all the practices and they tick them off the list. And somehow the systems just seem to be a bit too difficult to work with. You get all the classics like it's hard. You've got different parts of the system have relationships that you don't understand, or you change this over here and that breaks, or you're trying to understand some control flow and it sort of weaves its way through lots of objects and bits of the system that you've never seen before, or what you find is you want to use an object, and in turn, to be able to use it, you actually need to go inside it, which in some ways means that the definition of the object isn't clear enough. Or the other one is you want to refactor some code. You need to make a change for some new functionality. And you change this one little thing, and then you find a week later, your refactoring is sort of still spreading through the code like an epidemic. Has anybody not got one of those? Yes. Everyone's got it right.
Lucky.
So there are two systems that are not like that in the room. Or I misphrased the question, one or the other. But we're doing all the right things, aren't we? So we know a lot about things like solid. So solid is this sort of little collection of principles originally coined by Mike Feathers, about the sort of things that make objects sort of follow fundamental OO principles. So you get things like single responsibility. So the idea is that an object should have one responsibility, and that makes it easier to understand and to use in different places. Open-closed, that a class should be open to be extended in the right way, but not modified. So again, it's clear about what belongs in the class and what doesn't belong in the class. And then Liskov substitution principle, which is that if you have an object, you can replace it with a subtype without breaking the code. There should be a consistency of behavior even when you subtype, which again, not all code follows. Interface segregation. So the idea is that you be clear about which services an object supports, and that you shouldn't need to. All you need to deal with is the interface. You shouldn't need to go inside the class to see what's going on inside. And finally, dependency inversion, which says the object should depend on abstractions. So the idea is rather than high-level objects necessarily depending on lower objects, is that they all depend on abstractions, and that makes it easier to manipulate or to replug things together, rather than having to deal with always having to deal with the implementation detail. So we've got a nice set of solid principles there, and of course everybody does that all the time, so we can stop training on that. But there's something interesting about this, which is they're all talking about individual objects or classes or types or whatever. They're all focusing on the individual object. In fact, they don't even focus on that, they focus on the object's API. Actually, it's not even that. It's focusing on how the object provides its services. And these are good things to do. I'm not saying don't do them, but it's not enough. Because what this doesn't tell you is when you have a system of objects, how they fit together. And what we tend to see is there's a lot of this sort of thing where, I haven't got a pointer.
I can't reach.
Yeah. So here we are, that's the sort of stuff down there. There's a lot of worry, there's a lot of material on how to write individual objects. And a lot of stuff on large-scale system design. This bit in the middle is often sort of left to chance. We see lots of sort of anti-patterns, things we started to call things like spaghetti and meatballs. You know, it's the modern version of spaghetti code, where you have some objects, but lots of incomprehensible brittle flow. Well, the other thing we see a lot of is things like helper objects. So I've got my thing and my thing helper. What that actually means is I know my thing is getting too big, but I don't really want to break it down, so I'm going to extend that type with a helper type. And the two aren't independent, they always belong together. But what we've done effectively is overflowed a class that's getting too big and just sort of overflowed it into another class, and another class, and another class.
When working as an architect, once I was asked by a team, they're like, "Oh, we've got a something helper, and now it needs a helper. But we think that something helper is a bit of a silly name. What should we do?"
That's a clue. The other thing, we see things like wiring tangles. So we've got all these objects, but they're all, the way they plug together is configured outside the system in XML. Hands up who's got one of those. Right. Yeah.
Or even not in XML.
Or not in XML, even so. And what that means is, you know, the sort of stuff appears magically out of the container and you can't tell where it comes from. So you lose the feedback, which is that actually it's quite difficult to construct this. That's a clue. It tells me that there's some structure in here that needs rework. What I do is I just suck objects out of the sky, and it seems to work until you try and change things. And then what you do is you add reflection. So you can't even see the objects being created. It's just, you press a button and then these things appear out of nowhere. This cloud of objects appear, and you don't know where they come from or where they're going.
In those kind of systems, you may have a very explicit description of the connections between your objects, whether in XML or in code, but all your objects are being connected up in one place, and it's very hard to understand what the relationships mean, why are these things connected this way. You can't see the wood for the trees, as we say in English. You can't see the reason for these objects being connected up in all this code that actually does the connection.
So, again, if we go down this, we've got, if you can see that, at the bottom, there are some slightly higher level principles or design rules. Law of Demeter, which is basically, the short version says an object should only deal with things that it creates or that get passed into it. And that's slightly more complicated than that. And similarly, dependency injection. If I need a dependency, it gets passed into me. I don't pull it from somewhere I can't see. So that's good for getting objects and little clusters of objects. But again, it's still quite small scale. At the top level, if you can see that, there are sort of high-level design principles and patterns. Like Conway's, some of social, so Conway's law says that system structure tends to follow organizational structure. That's the short version of that. Things like the end-to-end principle, which is the found basics of the internet, which says that the nodes at the end do all the failure handling, and you have possibly unreliable pieces in the middle. We have REST, which is how you interact with the service. All these kind of high-level, or CAP, which is the justification for some of the NoSQL databases. So you have all these sort of very high-level things that tell you how the big pieces fit together, and you have some low-level stuff. But what about this bit in the middle? And there are some principles, not principles, there are some patterns of use at this level. Things like MVC for sort of doing certain kind of GUI things, or pipes and filters for signal processing, or ports and adapters, if you know that, used to be called hexagonal architecture, which they're patterns for certain kinds of system, and they belong in one system and not in another, because they serve a particular purpose. but they're not really underlying principles. So the question is, what would be some underlying principles that would help us think about what are good ways to deal with this code in the middle?
So before introducing a principle, we will talk about a principle, the principle of compositionality. But before that, I'll take a digression to tell a story about a system which wasn't awkward to work with, and which inspired sort of like some exploration that resulted in this talk, a reflection about why did this work so well. It was next slide. It was a financial calculation system for doing what was called scenario modeling of financial portfolios. So the idea would be you'd simulate a market crash scenario. For example, what happens if Cyprus stops people taking money out of its banks, by modeling how that might be represented in terms of shifts of a model of the market that you have in your financial institution. Then you revalue your entire portfolio, which is very compute intensive, and then you find out like how much risk exposure you have, how much money you might lose, that kind of thing, or make, you never know. So very compute intensive, large amount of technical infrastructure to run this across a big grid of compute nodes. What's interesting about this was what was happening inside these compute nodes. So to perform a valuation with a scenario, the sort of calculator agent was sent a request that contained the instrument to be revalued and a scenario to be applied. This message came in, it was turned into an immutable object that knew how to talk to services that the calculator had to gather data that was required for the calculation. So the message would know how to find a scenario object, it would know how to find data, for example, the instrument definition to be calculated against, and all the other information that it needed in order to perform the calculations that were requested. And then the scenario, which was an immutable object, as were all of these other pieces of input data, the scenario then was passed the input data and knew how to transform it into a modified input data that represented the scenario to be calculated, and then that modified data was passed to a pricing engine to be priced, and then that resulted in some results that got sent back out as a message. So when we started writing this, we implemented all these scenarios as classes of distinct types. We might have a Cyprus bank crisis scenario and Brazilian biofuels scenario and such like. And each class, it turned out, had a lot of similarity with other classes that were also modeling scenarios, particularly about how do we bucket up input data and shift them in different ways. And so we started pulling out all of this commonality, particularly the commonality of control flow, into objects. In Java, really the only way of capturing commonality of control flow is to pull it into an object that talks to other objects. So that's what we did. So we started composing these scenarios out of objects into like graphs of objects that would know how to talk to these services to pull in the data that they needed and to modify the data they needed. So this became, after a while, pretty much unmaintainable. So here's an example of a scenario composed out of lots of small pieces, and pretty soon we basically hit the wall of our ability to understand our own code. So the users was trying to ask us to make changes, and we would be struggling with code that looked like this. Something has to change. So we refactored again, but this time, instead of attacking the duplication, we attacked the clarity. So we, bring up the next slide. We pulled out all of that Java syntax to do with creating objects and plugging them together, and we hid it behind some static functions that basically represented why were these objects being plugged together, to try and explain what is being performed by these objects, rather than all the Java syntax of actually newing up objects and sticking them together. And this worked very well. So what we found was that,
That's right.
So we basically refactored our way to what Martin Fowler in his domain-specific languages book calls an internal domain-specific language. We were sort of using sort of Java to define a language, and then we were able to very quickly implement new feature requests from the users. They would say, can your system implement a scenario like this? And we were able to basically take their requirement and turn it into pretty much a word-for-word transliteration into Java code, but just with some brackets and commas and braces and things that Java makes necessary. So we had this situation where we could put together functionality very quickly from a request coming from the user to it running on the desktop with full unit testing and full system testing of all of the server infrastructure. It took about an hour, so we were able to have a very close collaborative relationship with our users, which was great. And this was because, so one thing that came out of this was, well, we didn't actually write any acceptance tests. We didn't capture examples in a BDD style. We just wrote down what they asked for because we were very confident. We'd unit tested all the little pieces of this DSL, and we had unit tested these classes that compose them into new pieces of DSL. And we'd also unit tested how they interacted with the services outside the language layer, and also all the system with system tested. And we were very confident then that if we just typed in what they wanted, the system did it. And we actually found no problems not having acceptance test levels at that level because we were representing what they wanted in their own language. But that kind of, as someone who wrote a book about starting with acceptance tests based on examples, that kind of bugged me a bit. And I've sort of been pondering since then why, what is it about this system and other systems that I've written in a similar way and seen other libraries and frameworks that have written in a similar way. What is it that makes that so that we had such confidence in composing it, modifying and changing it? My conclusion is that the design was not merely composing objects. The design had a property that is compositionality. So compositionality is a language design principle. It's used in programming languages and mathematical notations. And basically it says that a language is composed out of small pieces. You can consider those pieces independently. They have sort of well understood meanings on their own. And you also have rules for combining them into larger expressions or statements in that language, and those rules also can be considered independently, and when you compose them into a new statement or expression, that itself can then be considered as a unique thing, and they compose very predictably. And those bigger pieces then can be used and composed with other rules to produce yet more sophisticated expressions. And those expressions are understood purely in terms of the rules by which we've composed them and the meanings of those rules, the behavior of those rules. So there's no hidden special effects going between different parts of this language. You can understand the behavior by just reading what's on the page. And that makes it very easy to predict what a particular change will do when I make a purely syntactic change. It's easy for me to understand the behavioral change that will happen as a result.
Okay, so I'm struggling with this a bit. But I think we've seen this before. How about this? Does anybody not recognize this? This is, so this was actually a little script written by Doug McElroy in response to Donald Knuth's demonstration of literate programming, in which he wrote it's a word count program that took over 10 pages in Pascal with Pascal, I guess.
Yes.
With literate programming. This is the famous Unix pipe. What does this do? This firstly it takes everything that isn't a character, turns it into a new line. Then it makes everything downcase, everything lowercase. It sorts all those. It counts the number of occurrences of each value, and sorts all those, and then sucks out I think it sucks out one of the...
Takes the first n. Where
the first n of those. Anyway. But the point about this is that this is made up of little bits and pieces that get plugged together, each of which does one thing well, and an infrastructure that describes how they fit together. So your little bits and pieces are all these scripts here, or these programs, and when whoever it was wrote sort or translate or unique, they didn't have this program in mind. They had a feature that they needed that they packaged into a nice little component, and then they could rely on the infrastructure, the pipe infrastructure, to mix these all together into a new program. And in fact, you can take this, you can wrap it up in a shell script and turn that into a new program that follows the same rules. And you get this sort of hierarchical effect, or combinational effect. So perhaps I'm still a bit confusing. Perhaps you could take each element in turn, break it down a bit.
So, from the definition of compositionality, the principle, there are sort of 4 aspects that it asks you to think about. And those aspects are not things that we normally think about when we're doing OO design. They're not something that's usually talked about in the OO design literature.
Ready to go.
So there are, we have some primitive elements, the very atomic pieces of our language that we will then build up somehow. So in the Unix pipe example, we have sort and we have tr, which does translating of characters. We have a way of composing those things, those primitive elements, into some new element type or new element behavior by some operator. So we have a composition operator that, given some primitive or maybe some compound pieces, will give us a new piece that has a behavior that we can understand from just looking at the pieces and the composition operators that we've used to build it. Then we have meaning, that is, what do each of these elements mean? When we were writing the large financial system, we used test-driven development to basically define what each of these pieces, how they would behave, what it meant to write a particular piece in this little DSL. But meaning in a compositional design is independent. Each piece has to have an independent meaning that you can understand independently of the context in which you might use it. TR has, in the sort example, has a behavior that is independent of the program, the shell pipeline or script in which I'm going to use it, and that allows me to then compose it with confidence. And pipe has a meaning of how 2 programs in a shell pipeline will be composed together. And again, I know that I can use that pipe with lots of different programs without having to worry about which program I'm composing. And then finally, syntax. How do we explain in our code what a composition of these pieces actually means to a human reader? So what notation are we creating and how, in order to express what these things do and why they're doing it? So that's quite different from sort of normal composition of stateful objects. If I, using dependency injection, take 2 objects and I compose them together by using setter injection or constructor injection, for example, then I can't now consider those 2 objects independently. I've got 2 objects that are stuck together. I don't have a new concept which I can consider on its own. If I want to think about the behavior of these 2 objects that I've composed with dependency injection, I have to understand the behavior of them both all the time, and maybe worry about what's going on inside one and how the event flows are flowing between them and where state changes are happening that might affect one another.
Okay, so if we've got all those pieces, how do they fit together? And one thing we realized as we built several systems this way is that you end up with a part of the code where you assemble, if you like, you assemble the system, you assemble the machine, you assemble the behavior from all these little objects that have, either behavior or composition aspects or whatever. But the thing is with that part is that it has to be mutable, because having state changing in there is just too hard to deal with and too brittle and too dangerous. So where does the state belong? What you find is you have the behavior in one part assembled out of immutable objects, And through that, if you like, flows the state of, the particular event that you're dealing with now, the runtime state. And so you separate the two, and you have a context that passes through behavioral code, and that's where you carry the state. And this is very much like, this is what the functional languages do, is that although, there's all this stuff about how functional languages are, immutable and stateless and all the rest of it, that only works because there's an awful lot of work going on in the runtime to make that actually happen. And it's, in many situations we have to do that by hand because we can't, or by design, because we can't rely on the runtime. But if you are in a land where you're using something like, or a situation where you're using something like Clojure, or Haskell, or take your pick, that's what a lot of that runtime is about. And one way to think about this, it's a bit like, sort of metaphorically, it's a bit like garbage collection. So for those of us who've been working in garbage collected languages for a long time, is that we no longer have to worry about memory management in the body of our code. There's a runtime, which is very complicated and clever, and it takes care of all of that, and we just don't see it anymore. In the functional languages, there is state, but that's down in the runtime, and we just don't see it anymore until it all goes wrong, but that's another question. And when we're building systems in languages that don't have that support, or environments that don't have that support, to some extent we have to do it ourselves, but at least we have the understanding of how to structure our systems and how to structure the mid-level code, if you like, to make that work.
So we are, I guess, moving complexity away, from one part of the system and moving it into another part of the system. But as a result, the part of the system we want to change the most becomes much more predictable and smaller. So a Haskell program, for example, can look like it's working with immutable data. There's 50,000 lines of C in the runtime that's targeted by 140,000 lines of Haskell code in the compiler to generate code that calls into that runtime, to give you the illusion that you're working with immutable data. So a lot of complexity, a lot of sophistication. The result is the way you're working is easier, more elegant, more predictable to make changes in.
So the other part of this is this notion of domain-specific language. And again, this is much easier in some environments than others. I mean, a lot of the stuff we do in Java is to make it actually look like different languages that some might think are better. But one of the things we've learned about this is is not to try and solve the world. Is you have, in any code base of any size, there'll be sort of various domains that you deal with. And the idea is that you localize the behavior for each particular domain, and you don't try and provide a universal solution. And there are two ways, and we found that there's loosely two ways to get there. One is this example, where you start at the bottom and you refactor and refactor and refactor, and you go, oh, that's what I meant. There's another way, which I've certainly worked on, which is where it's called program. I mean, it's an old name called programming by wishful thinking. So I write the code that kind of looks like how I want it to look, and then somehow figure how to implement that. And they both have their trade-offs. But the point is at each point, the thing that matters most is being expressive and describing as closely as possible to the domain you're working with. And there's obviously a very close relationship with domain-driven design, but with the difference is that we're, rather than thinking in terms, if you like, it's not just thinking in terms of nouns and verbs, it's thinking in terms of sentences, and how do the nouns and verbs fit together in this domain.
So in the large financial system I talked about, we used this technique to define the financial domain that the system was performing, but also we used a similar technique, similar style in the parts of the code that built protocol stacks by which these parts of the system communicated. The part of the system that generated the reports would have like a little mini internal language for describing reports and so on. So large systems are made up of many domains, some technical, some in terms of the application domain, and that application domain may be split up into many subdomains, and we can target a specific language at each part of that, each domain of that larger system, so that we don't try and just solve everything with one Uber language, we can create expressive notation for different parts of our system.
So the reason we bother with this is we find it easier at some level. It lets us decompose our code into smaller units, that squeeze out the duplication. And then from those units, we can build up new units and be confident that those things that we build up will be reliable and predictable. We can actually understand them. So each unit of code, whatever it is, deals with one concept. And it's all about dealing with complexity. It's pushing implementation at this level out of the immediate code into sort of some supporting space, and then doing the same again, and then doing the same again. So that at each level you have this sort of consistency of language, and you know what you're dealing with. And you don't find yourself, this notion of leaky abstractions, you don't find yourself dealing with financial whatevers, and all of a sudden there's some messaging thrown in. Or all of a sudden there's some memory management thrown in, or something like that. You just deal with, you deal with domain code, and everybody can see, and in an ideal case, including the end users, can see what's actually going on there.
So I have actually used this technique also for writing exceptions tests in other projects, and have been able to sit down at the Java IDE with a business analyst who doesn't understand Java, but by basically making all the Java syntax very pale grey and making all the words black, it does look like a clear description of a business requirement, and they're happy to collaborate with developers writing those kind of tests to get their requirements into the exceptions test suite. So you can use tricks like that to make these languages more expressive to people who are not technical. But of course, the goal is not to make a notation that is easy for someone who doesn't understand the notation to understand. If you look at the Unix pipes example, you have to know what tr-c or unic-c means in order to understand those 6 lines of code. So what we're trying to achieve is a notation that is in which we can make changes very predictably and very easily. Even if you have to learn what that notation means, once you've got up that learning curve, you can then manipulate statements, expressions in that notation with great ease.
So, just to wrap up, do you want to explain what this is?
Well, this is a picture of a building in Montreal called Habitat 67 that was built in 1967 for the World Expo. But it's an entirely modular building. So each of those pieces is the same, but they've been positioned into the building when it was built in different configurations. So all the actual houses, all the flats in the building are all slightly different, but they're all made out of almost identical pieces. So I guess this style expresses some kind of philosophy of how we approach programming in a way. Even if we don't explicitly think about it, whenever we're writing code, we are building a new language or building on the language that we have. And then those, whether we're just writing functions or classes or we're thinking more compositionally, the code that we write becomes part of the language for the next bit of code that we're going to write on top of that code we've written that's going to call into it. And so, we're always building up little languages as we work that become, a base little language for the next layer of the system that we're writing. And that layer becomes a little language for the layers above it, and so on. And so, at the very bottom of this, we've got a programming language that follows the principles of compositionality, because that's how we understand the behavior of, say, what semicolon means in Java, or what function composition means in Haskell. And so, if that's a guiding principle at the very lowest layers of our system, as we build up new layers of language, we should, we're arguing, we should be following the same principles, so that our systems remain predictable to change, and we don't have these problems that Steve was talking about at the start of the talk, where changes cause unexpected and unpredictable ripples across our code base, or unusual and surprising bugs will suddenly appear as we make changes in one part of the system. So, thinking about programming as a language building, language defining exercise, it never stops. It's turtles all the way up as we are designing these languages. And so, we're arguing that the principle of compositionality that underlies language design is a useful guiding principle for the other layers in our system that we're writing ourselves.
That's it.
And that's it.
Thank you.
Thank you very much.
Do we do questions or comments? So there's one over there, thank you.
In the DSL that you just shown with the predicates and everything, was it the case that every predicate didn't have any side effects? Because
there's two aspects to this. One of which is, so here is a model of the Cyprus banking crisis, and it says, okay, so we've got some shifts of yield curves to say, okay, borrowing in the euro, well, you're going to start losing money, or you're not going to make so much money, and probably not quite make quite so much money if you're borrowing in pounds, but the dollar is going to be good because you're getting a boost from the crisis in Europe. Right, so that's saying, how do I model this in terms of transforming a yield curve? But that scenario is also used to go out and get those yield curves. So the immutable object that described the DSL had polymorphic interfaces and could talk to the polymorphic interfaces of the context in which it was running. So it would pull data in through caches and therefore, basically have some state-changing effect behind the scenes. But in terms of what this meant, yes, it was purely immutable and purely functional. Does that make sense?
predicates that don't have side effects, and if you do try to do that, you kind of further yourself from the very descriptive DSL, which even the business people can learn. And if you don't do this, and you have side effects, and you don't find them, and you don't know them, the moment you change, you can have catastrophic effects. Like if in the building case, if you were to remove some blocks, it would have been fine. Some blocks would just make the whole building fall apart.
Yes.
So I think it's a compromise, in my opinion. And
yeah. So I think that having the principle in mind will, helps guide thinking about design and make you think about those issues that might come up, and then you can make an engineering trade-off. Is it worth the risk of introducing aliasing effects by having some explicit state in my language elements, or is it worth avoiding that and moving state out into something that knows how to interpret this and try and avoid that? And so principles aren't things you should follow without thinking. They're guiding principles that help you see where problems might arise and then make the right decisions about them.
Okay. Anyone else? Oh, yeah.
I was just wondering if doing this sort of thing you run into cases where the border between different domains isn't clear, and in that case, how do you deal with that?
Yes, I guess I haven't. It's been pretty clear where the boundaries of these languages lie. But sometimes I've got a little language that does one thing, and it obviously fits into a language about something else because the domains relate. So you can make one language build on top of another, and use different languages can call into one another, relate to one another that way. But I guess if I did have like this fuzzy domain boundaries, maybe I'd just start off with one great big language and then work out as I go where it's best to slice it.
And the other thing I'd say is that's true for regular code as well. And a lot of the problems that we deal with is where you have regular code and there's sort of straight through with bits from one domain and another all sort of mixed up. And at least once you start teasing things apart, often it makes it easier to see, at least to see it, even if you can't fix it. Sorry, is there one over there?
No? Okay.
All right, I think that's it. Time for lunch. Thank you very
All
much.
right, thank you very much.